Hello there, Mr. Sutton here, bringing you the AB Calculus Quiz 4 Extra Practice Solutions on motion and related rates. For this set of problems, we have a model rocket being fired upward with a position given by this S of t function, and we've got feet for distance, seconds for time. First part of the problem, we want to find velocity and acceleration functions. For velocity, we just need the derivative of position, so that's going to be s prime, which is going to be 192 minus 32t. Acceleration then is just going to be the derivative of velocity, or the second derivative of position, so that just becomes negative 32. For this part, we want to know the maximum height of the rocket, so we need to know critical values for s prime. So s prime, or also the velocity, again, that was 192 minus 32t. That's going to equal 0 at, well, let's see here. If I subtract 192 and divide by negative 32, this is a calculator question, so let me check that out. So it looks like that's going to come out to 6. Okay, so that happens at time 6. So that is the only critical value we've got here. If it happens to be a local max, then that will prove it's also the absolute max height. To figure out if it's a max or a min, we can take the second derivative and plug 6 into it. Now recall the second derivative, s double prime of t, that was just negative 32. So if you plug 6 into the constant negative 32, you're still going to get negative 32 back, which is kind of nice. Since this is negative, that means that the s function is concave down, which means our critical value is at the top of the frown, so we just found a local max. Since it's the only critical value, that also makes it an absolute max. So our max height is going to happen at time 6 seconds. They didn't ask when it was going to happen, though. They asked what it was. So to figure that out, we need to actually plug it back into the s function. And I'm going to go ahead and do that on the calculator now. To make this a little bit easier to look at, I'm going to actually enter my s function in the y equals under y1. And then I'll just quit out of here. And I'll just do alpha trace to pull up my y menu and select y1. Open a parentheses and just plug 6 right in there. So now I don't have to worry about PEMDAS or anything else. And that's going to come out to 576. And since this is height, this is going to be 576 feet. For this part of the problem, we want to know when the rocket will have equal velocity and acceleration. So recall my formulas. We have a velocity formula of 192 minus 32t. And we want to know when that equals the acceleration formula of just minus 32. So if I subtract 192, that's going to give me, well, let's see here. Let me just do this on the calculator. So we have negative 32 minus 192 comes out to negative 224. And then if I divide that by negative 32 to get t by itself, that's 7. So that happens at time 7 seconds. For this problem, we want to know when the rocket's going to hit the ground and what the velocity will be at that time. So let me start by just taking s of t here. And hit the ground means that we have a height of 0, position of 0. So that's going to be 0 that we set that equal to. And we can solve this by factoring here. These are both actually divisible by 16, believe it or not. I mean, 16 goes 10 times into 160, so if you're taking it out of something that's 32 greater, you're taking it out of you're going to get a 12 when you take it out. So taking out then 16, I'm going to end up, or 16t, I'm going to end up with just 12 minus t, all that equals 0. And then we very quickly see that t is either going to be 0 or 12. Now we want to know when the rocket's going to hit the ground. Probably time 0 is not a very good answer because the rocket hasn't been fired, so the idea of hitting the ground, before you've been fired off, this seems kind of silly. So we're going to use 12. We're going to count 12 here. So 12 seconds is when we hit. And then what will the velocity be at that time? So we have to plug 12 into our velocity function. So that's going to be 192 minus 32 times 12, which I'll do on the calculator. There it is, and all that's going to come out to negative 192, and it's velocity, so that'll be feet per second. For this set of problems, we have a particle moving along a line with a position given by this s of t function, which is a cubic function. We want to know when the particle is going to change directions for the first part here. So for that, I need to know when the velocity is 0, And for velocity, I need s prime. So that's going to be 3t squared minus 10t plus 3. So let's find out when this equals 0. Now, I can figure this out by factoring. I can split this up into, let's see, this is going to be a 3t times a t. And the only way to get a positive 3 is if I'm multiplying 1 and 3 together. They're going to have the same sign. Since the middle here is negative, I'm thinking it's going to be a negative 1 and a negative 3. And I probably could have factored this a little bit more already if it was 3t minus 3. So I'm going to do 3t minus 1 instead. So 3t minus 1 times t minus 3. If you just want to check, though, 3t times negative 3, that's negative 9t. Negative 1 times t is negative 1t. Negative 9t plus negative 1t gives us this negative 10t in the middle. Now that we've settled that, we see that this equation is true if t equals 1 over 3 or positive 3. But we don't know that the particle actually changes directions. These are just possible direction changes, critical values. To figure out if it actually changes directions, we need to put these on a number line, a v of t number line. So there's 1/3 and 3, and we need to do some sign analysis around these. So let me pick a number less than 1/3. I'm just going to go with 0. Why not? And then plugging that in here, that's going to be a negative times a negative, which is a positive. And I'm just going to use this factored version of v. A number between 1/3 and 3. 1's pretty easy. So that gives me a positive and a negative, which is negative. And finally, bigger than 3, let's go with 4. That's going to be a positive. Positive comes out positive. So we see here that v of t does indeed change signs at 1/3 and 3. Therefore, we have direction changes at 1/3 and 3 seconds. For the second part of this problem, we want to know the acceleration at the times that we got for answers in part A, basically the places where we were changing direction. So recall from part A, this was our velocity formula, and these are the two times, 1/3 and 3 seconds, where our particle changed directions. So to figure out the acceleration there, we need the acceleration formula in general. A of t is going to be v prime of t, which is going to be 2 times 3, so 6t minus 10. All we have to do now is just plug in 1/3 and 3 into this function. So we have a of 1/3 to start with. That's 6 times 1/3 minus 10. Well, that's going to be 2 minus 10, which is negative 8. And this is going to be in feet per second squared. Next, we're doing acceleration at time 3. That's 6 times 3 minus 10. 18 minus 10 is positive 8, and again, feet per second squared. On this problem, we want to know the velocity and acceleration at time 5, and also whether our particle is speeding up or slowing down at this time. So recall from parts A and B, our velocity formula and acceleration formulas were as follows here. 3t squared minus 10t plus 3 and 6t minus 10. So let's do velocity at time 5, basically plugging 5 into this velocity function. Just going one term at a time. This is 3 times 25, so 75, minus 50 is 25, plus 3 is 28. That'll be feet per seconds. Acceleration at time 5, now we're just doing 6 times 5 minus 10, which is 30 minus 10, or 20 feet per second squared. As to the question of whether we're speeding up or slowing down, we have to compare the signs of v of 5 and a of 5, velocity and acceleration. We see that the velocity is a positive, so is the acceleration. Since v of 5 and a of 5 have the same sign, this implies that since they're working together, the particle must be speeding up. For this set of problems, we have an object going in a straight line, traveling with this position function here. First part of the problem, we want the object's velocity at time 6. All right, well, let's go ahead and take the derivative of s to get our velocity function. That's going to be 3t squared minus 24t minus 54. And to get the velocity at time 6, I just have to plug 6 into this function. Let me just do that on the calculator. So plug in 6 into all of that. We end up with negative 90, and that's going to be in feet per second. For this problem, we want to know the object's average velocity for 6 seconds, the first 6 seconds. So AROC, we basically have to do s of 6 minus s of 0 over 6 minus 0. To help me with that, let me go to the calculator. So to start me off here, I've just entered the s function as my y1. And then let me just quit out of that. So let me just do alpha trace y1, and I'll just plug 6 into that to see what that comes out to. Negative 540, okay. And s of 0, well actually these all have variables, t's, so that's going to zero out everything. So we just end up with negative 540 over 6, which, if we wanted to reduce it, is going to come out to negative 90. So that's going to be negative 90 feet per second. On this problem part, we want to know when the object's traveling at a rate of 6 feet per second. So we want to know when the velocity, which was this function again from part A, takes on a value of 6. So this is just a quadratic. Let's just zero this out and solve it that way. So we can subtract 6 from both sides. That'll give me a negative 60 over here. And looks like I can factor a 3 out of all this. So that's t squared minus 8t minus 20. All of that equals 0. Two things that multiply to negative 20 and add up to negative 8. We can use t plus 2 and t minus 10. So we see here then that t equals negative 2 and positive 10. So in terms of when the object's traveling at this rate, presumably this is going to be positive time that we're talking about. So this negative 2 is kind of a bogus answer. I'm just going to settle on 10 seconds as my final answer here. For this part, we want the object's acceleration at time 6. Recall the velocity from part A was this formula. So the acceleration is going to be the derivative of velocity, v prime. So that's going to be 6t minus 24. And if I plug 6 into that, I've got 36 minus 24, which comes out to 12. So that'll be feet per second squared. For this problem, we have a spider bite creating a circular area of infection. If the radius of the infected area is 3 millimeters, growing at a rate of 1 millimeter per hour, at what rate is the infected area increasing? So we have a rate of a radius changing, and we have a rate of change for an area. Because we have multiple rates and they're all related, this is a related rates problem, we have to come up with a formula that ties all of this stuff together and then take its derivative with respect to time. Well, since we're talking about a circle and we're talking about area, how about the circle area formula? A equals pi r squared. So taking the derivative of this with respect to time, we've got dA over dt equals, just using the power rule now, 2 pi r times dr over dt. And what are we all ultimately solving for? We want the rate of change of the infected area. So dA over dt is actually what we're solving for, which means we need to plug things in for r and dr over dt. Well, r is the radius at the point in time that they ask the question. So they said the radius of the infected area is 3 millimeters. So this is our instant value of radius, 3. And then growing at a rate of 1 millimeter per hour, this is dr over dt that they're giving us, this 1 millimeter per hour, so that's 1. Multiplying this out, this is going to be, obviously 6 pi, or if I get a decimal, let me see what that is. So here's my decimal for 6 pi, about 18.850 if I round to 3 decimals. And what's the units going to be? Well, dA over dt, area, that is millimeters squared on this one. Time is in hours, so this is going to be millimeters squared per hour. For this problem, we have a boat pulled into a dock by a winch 12 feet above the deck of the boat. And let's see, the winch pulls in a rope at a rate of 4 feet per second. Determine the speed of the boat when there are 13 feet of rope out. Okay, so for this one, a picture is going to help. So here's a triangle kind of situation. We have a boat over here. This is the dock right over here. We have a boat that's being pulled towards the dock, and it's being pulled by a rope that has a winch, a pulley that's all the way up here. So there's our winch, pulling in the boat toward the dock. Now we've got a few dimensions on this. We don't know how far the boat is from the dock, do we? Nope. So this is going to be an x, an unknown. However, they did tell us that this winch was 12 feet above the deck, and that's going to be a fixed value. That's not going to change. Like this x value here, this is going to change as the boat moves closer. So is this rope length up here, which I'm going to call z. But this 12, we can take this to the bank. That's never going to change. So we're talking about the speed that the boat is coming towards the dock. That's the rate of change of x. they're telling us that the rope is being pulled in at a rate of 4 feet per second. They're giving us the rate of change of this z side here of this triangle. So because we have related rates, we're going to have to come up with a formula that ties all of this together and then take the derivative with respect to time so that we can access all those different rates of change. So I've got a good formula for this since I have a right triangle here. How about the Pythagorean theorem? X squared plus 12 squared equals z squared. So taking the derivative of this, we've got derivative of x squared, which is going to be 2x times dx over dt. Derivative of 12 squared is 0, since that was a constant. Derivative of z squared is going to be 2z dz over dt. And we're ultimately solving for dx over dt. And they said speed, so we want the absolute value of that. So we have to find things to plug in for x, z, and dz over dt. Now, x was the distance of the boat from the dock at the point in time when this problem happens. We don't know that distance yet. However, we do know that there's 13 feet of rope at the point where this problem's happening. So we've got two sides of a right triangle at this point in time. We can use Pythagorean theorem right here just to solve for this x side. So I can write x squared plus 12 squared equals 13 squared. So then x is going to be the square root of 13 squared minus 12 squared. This is the square root of 169 minus 144, square root of 25, which is 5. So the boat apparently is 5 feet from the dock at the point this problem's happening. So we have 2 times 5. We don't know dx over dt yet. That's what we're actually solving for. Z is the length of the rope, which they said was 13. And then dz over dt, that's the speed the rope's being pulled in at, which is 4 feet per second. And, I mean, technically, since this z side is getting shorter when I pull this rope in, I could write this as a negative. However, because we're also talking about the rate of change of this x value, which is also going to be decreasing, if I keep this positive, then my answer for x is going to be a positive, which is going to end up giving me the speed that I need for the answer for this problem. All right, so we can really just solve for dx over dt if we multiply the stuff on the right and divide by this 10. Well, the stuff on the right here, this is going to be, let's see, this is 26 times 4 is going to be 104. Yep, that's right. And then if we divide that by 10, 104 divided by 10 is going to be 10.4, and that's going to be in feet per second because x is measured in feet and t is measured in seconds. So 10.4 feet per second. On this one, altitude of a triangle is increasing at a certain rate, and the area is increasing at a different rate. So we already got more than one rate involved. It's probably a related rates problem. We want to know at what rate is the base of the triangle changing given an altitude of 10 centimeters and an area of 100 square centimeters. All right, so what we're going to do here is basically set up an equation that ties all of these quantities together and then differentiate with respect to time. That's going to let us access these different rates of change that we're being given and being asked to find. So a good formula for this one, since we're talking about the area of a triangle, would be the triangle area formula. A equals 1/2 base times height. And I'm just going to go ahead and take the derivative of this thing with respect to time. So derivative of A, that's going to be dA over dt. A is a function of time. And we're going to have to do the same thing for B and H. But because these are two different functions, we're going to have to use the product rule. So let me set up the box and ribbon for those. For one of my factors, I've got 1/2 B. For the other one, I've got H. And the derivatives of those, we're going to have 1/2 dB over dt, because base is a function of time, and also dH over dt. H is a function of time. Using the ribbon to multiply those together, we have dA over dt equals 1/2 H dB over dt plus 1/2 B dH over dt. And at this point, it's time to plug things in and see what we're solving for. Now, they wanted to know at what rate is the base of the triangle changing. So ultimately, we're solving for this dB over dt part. So that means there's, let's see, 1, 2, 3, 4 things that we need to find values for in order to solve for dB over dt. All right, well, starting on the left here, dA over dt, that's the rate of change of the area. They said the area was increasing at a rate of 2 square centimeters per minute. So dA over dt can be substituted with 2. And then for h, well, they gave us the altitude. That's going to be 10 centimeters at this point in time. So this equals 1/2 times 10 times dB over dt, because we don't know that yet. That's what we're solving for. Now, how about the base of the triangle? Well, they didn't give us that, but we can work backwards to find it. We know the area of the triangle. We know the altitude, so we can use 1/2, or area equals 1/2 base times height, to solve for the base. We can write 100 equals 1/2 base times 10. And then working backwards here, let's see, divide both sides by 10. We have 10 equals 1/2 b multiplied by 2. We end up with b equals 20. So we're going to have plus 1/2 times 20. And dH over dt, that's the rate of change of the altitude. They told us up here the altitude was increasing at a rate of 1 centimeter per minute. So dH over dt is going to be 1. So there's that. And now let's just clean this up a little bit and solve for dB over dt. So we have 2 equals, let's see, this is going to be 5 plus 10. And if I subtract 10, that's negative 8. Negative 8 divided by 5 is going to be negative 1.6. And for the units, that's going to be, let's see, base is measured in centimeters, time is measured in minutes, so negative 1.6 centimeters per minute.